In this module, we shall look at the risk difference and the risk ratio. So this is essentially a comparison of two proportions. You have seen how it is possible to compare two proportions using either a normality test based on asymptotic theory or an exact test such as Fisher's exact test. You have seen this in your undergraduate classes in statistics as well as in the papers on inference in the postgraduate classes. Here we shall look at the same thing but from a slightly different perspective. Now, many of these tests have developed independently in the context of epidemiology. So our position in this module is that we have a 2x2 table. A 2x2 table is one of the basic units of measurement in epidemiology. It arises when we are considering the effect of an exposure on a disease, and here we assume that we have a binary exposure, that is, an exposure which can be classified as yes or no, and also a binary disease, that is, we have classified individuals based on whether or not they have the disease, yes or no. So, for example, we can look at smoking and lung cancer. In this case, we observe for each individual whether or not they smoke and whether or not they have lung cancer. So, being given this 2x2 table, we wish to make a statement about the association between exposure and disease. There are various ways of doing this, and in this module, the two concepts which we shall explore in more detail are the risk difference and the risk ratio. For the sake of comparison, we shall also look at another very popular measure of association called the odds ratio, and finally we shall also look at a measure called the number needed to treat, which is commonly derived from the risk difference and risk ratio and is of value to epidemiologists. Learning objectives for this module. We shall first look at absolute versus relative measures of association. We shall next define the risk ratio and the risk difference and see that while one measures absolute association, the other looks at relative differences. For the sake of comparison, we shall define the odds ratio, and finally we shall look at two related epidemiological concepts, which are the number needed to treat and the attributable proportion. The risk ratio, or RR, and the risk difference, RD. Let us first look at the concept of ratio versus difference, assuming that we have data from a cohort study. When I say cohort study, I mean the most common and recommended study design in epidemiology, which is that we start with two cohorts, one of which is exposed to a particular exposure of interest, so say this cohort smokes, and the other does not smoke. So the idea is that we have a binary exposure, we have individuals who are all disease-free at the onset of the study, and we're going to follow them up over time to see how many of them develop the disease of interest. So from the perspective of a statistician, we have an exposure which is binary, that is, can be classified as yes or no, and we have an outcome which is also binary, that is, we can classify individuals as whether or not they develop the disease of interest or not. So this is the simplest starting point in epidemiology. Being given this disease, there are two ways to compare the measures of association. So the first would be to form a ratio. That is, we look at the percentage of people or the proportion of people who develop the disease in either of the groups, and we form the ratio of this to compare the relative disease occurrence in the two groups. Alternatively, we could look at the difference. That is, we find the proportions which develop the disease in the two groups, and instead of dividing the proportions one by the other, we look at the difference of the two proportions. Now, the two measures will convey different information and are used for different purposes, as we shall see in the following slides. In epidemiology, we can take the difference in the case when the proportion represents either an incidence, which is the occurrence of a new disease, or a prevalence, which is the number of the proportion of existing cases. However, it is relatively uncommon to use ratios or differences based on prevalence and more common to consider the incidence. The ratio is a relative measure. That is, the ratio tells us how large the incidence is in one group relative to the other. What it does not tell us is that it tells us nothing about the absolute difference between the two incidences. So, for example, suppose we have conducted the previous study related to smoking and lung cancer, and we calculate that the risk ratio is equal to 2.0. Now, a risk ratio of 2.0 could be obtained by a cumulative incidence of 4% versus 2%, or it could be 20% versus 10%, or 80% versus 40%. Now, note that in either case, when we take the ratio of the incidences, the ratio turns out to be 2. However, if we take the absolute differences, in the first case, the absolute difference is only 2%. In the second case, the absolute difference is 10%. And in the third case, the absolute difference is 40%. So, although we get the same information about the ratios, we do not get any information about the differences, and it is up to us to decide whether it is more important to look at the ratio or the differences in this situation. The difference is an absolute measure. That is, the risk difference is an absolute measure because it conveys how much one group differs from the other in the scale of 0 to 100%. I mentioned the concept of a 2x2 table in my introduction. So let us assume that we have a 2x2 table. That is, we have group 1, which we say are exposed to a particular exposure of interest. So again, let us assume that this exposure is smoke. And we have group 2, which say is the group which does not smoke. For each of group 1 and group 2, we follow them up over time, and at the end of the study period, we look at the number which develop the positive outcome and the number which develops the negative outcome. We can summarize the total information in this 2x2 table, which is a basic unit of epidemiology. So A, for example, is the number in group 1 who develop the positive outcome. So in this case, in our example of smoking and cancer, it is the number of smokers who develop lung cancer. D is the number of non-smokers who do not develop lung cancer. And similarly, we can interpret C and B. So here we have a 2x2 table, and we can also see the marginal frequencies A plus C, B plus D, A plus B, C plus D, and so on. The total sample size is A plus B plus C plus D individuals who have been followed over time. Having been given this table, we wish to compare group 1 and group 2 in terms of the chance of developing the positive outcome. So again, if we go back to our example of smoking and lung cancer, we would want to see if the incidence of lung cancer is different for smokers and for non-smokers. The title of this slide is Relative Risk, Risk Difference, and Odds Ratio. And these are just 3 of the measures which we can do to find exactly this. The relative risk for the preceding table would be given by RR equal to A by A plus B by C by C plus D. So A by A plus B is the proportion of people who experience the event in group 1. C by C plus D is the corresponding proportion in group 2, and A by A plus B divided by C plus D is the corresponding ratio which we call the risk ratio. Now when we compute such a quantity in statistics, we would always want to test for its significance, and for this purpose we need to find the standard error. It turns out that instead of finding the standard error of the RR, it is easier to find the standard error of the log RR, and you can see from the definition of the RR, taking logs would reduce it to the sum and difference of 4 functions. So log of RR is log of A minus log of A plus B plus log of C minus log of C plus D. And we can use the delta method to find the standard error of log RR, which is given by square root over 1 over A plus 1 over C minus 1 over A plus B minus 1 over C plus D. Now note that because we have assumed that group 1 and group 2 are independent, the proportions A by A plus B and C by C plus D are also independent, and hence there is no covariance term. Thus, when we implement the delta method, we just need to implement the univariate and not the multivariate form of the delta method. We can use RR divided by the standard error of RR to test the hypothesis of whether or not RR is equal to 1. Equivalently, we can use log RR divided by the standard error of log RR to test the equivalent hypothesis of whether or not the log RR is equal to 0. So RR equal to 1, as you can see, would tell us that the proportions are identical in the two groups, or there is no association between exposure and disease. Now, if we reject this null hypothesis, we would like to quantify the extent of association, and we can do this by finding the 95% confidence interval for the RR, which we can do on the log scale and then exponentiate back to find it on the RR scale. So the 95% confidence interval for the RR is given by exponential of log RR minus 1.96 into SE log of RR to exponential log RR plus 1.96 into standard error of ln RR, where RR and the standard error of log RR are as given in the previous two lines. The risk difference in this case is given by RD equal to A by A plus B minus C by C plus D. That is, it is the difference of the incidences in the two groups. Using similar arguments as before and the delta method, it is possible to show that a 95% confidence interval for the risk difference is given by the risk difference minus square root over P1 minus L1 square plus V2 minus P2 square to RD plus square root over P2 minus L2 square plus U1 minus P1 square. So P1 and P2 are the two proportions here, and L1, L2 are the lower confidence intervals for each, and U1, U2 are the upper confidence intervals for each. Now you know that it is possible to derive L1, L2, U1, U2 based on the asymptotic difference of a proportion. So this confidence interval for the risk difference has been suggested by Armitage et al. A difference standard error proposed by Deeks and Higgins is of the form standard error of RD equal to square root of AB by A plus B cubed plus CD by C plus D cubed. This standard error is popularly used in meta-analysis. For the sake of comparison, another very common measure used in such tables is the odds ratio. The odds ratio in this case is given by OR equal to A by B by C by D, which we know will simplify to OR equal to AD by BC. As before, we can take the log of the OR and see that log of OR is equal to log A plus log D minus log B by log C. Using the delta method, it is possible to show that the standard error of log OR is given by the symmetric form, which is square root over 1 over A plus 1 over B plus 1 over C plus 1 over D. As before, we can use the OR divided by the standard error of the OR to test the hypothesis H0 OR equal to 1, that is, there is no association between exposure and outcomes. Equivalently, we can use the log OR divided by the standard error of log OR to test the hypothesis of the log OR is equal to 0. If we reject the hypothesis, then we want to construct a confidence interval for the OR, and as before, the 95% confidence interval is given by exponential log OR minus 1.96 into standard error log OR to exponential log OR plus 1.96 standard error log OR, where the standard error of log OR is square root over 1 over A plus 1 over B plus 1 over C plus 1 over D as given in the previous line on the slide. A couple of notes. One, as you have seen in any exercise on the frequency chi-square, that there are problems to the standard asymptotic assumptions in cases when we have 0 or near 0 values in any of the cells. So in the case where we have 0 values or near 0 values, a common practice recommended by Deeks and Higgins is to add 0.5 to all the cells A, B, C and D. Such tables often arise in meta-analysis, that is, studies where we have a large number of studies of the same disease association and we wish to combine them to get one summary measure of association. In such studies, usually any study where A equal to C equal to 0 or B equal to D equal to 0, these are excluded from the meta-analysis. For more, you are reference to Higgins and Green. A number of references for further details on the use of the risk difference, risk ratio, meta-analysis and so on. The first is the book on practical statistics for medical research by Chapman and Hall by Altman. The second is to the very common book, very popular book by Armitage in 2002, Statistical Methods in Medical Research. The reference for Deeks and Higgins is to their JPT paper in 2010, Statistical Algorithms. You can also look at the book on proportions and their differences by Newcomb et al. And finally, for a good review of the use of these in biostatistics and epidemiology, you can refer to the textbook by Pagano and Gavro. Let us next move on to an illustration of the uses of relative risks, odds ratio, risk difference, and the number needed to treat, which is a related epidemiologic concept, using a review paper by Tripepi et al., which appeared in Kidney International in 2007. So one of the motivating examples which has been presented in this paper is the 2x2 table, which looks at two groups. One group which was randomly allocated to a drug called Rampiril and is given in the first row of the table, and the second is a comparison group which is randomly allocated to placebo. Both groups were followed over time, and in the first group there were 4,645 subjects. In the second there were 4,652. They were followed over time, and it was found that in the first group 651 developed cardiovascular events, while the remaining 3,994 did not develop any cardiovascular events at the conclusion of the study. In the second group, 826 developed cardiovascular events, and 3,826 did not develop any such events. If we calculate the corresponding proportions, we can see that the proportion of patients with CV events in the Rampiril group turns out to be 0.14 or 14%, and the proportion of patients with CV events in the placebo group is 0.18. The risk ratio is thus 0.14 by 0.18 equal to 0.78, suggesting that Rampiril is protective against cardiovascular events. To see if this difference is statistically significant, we can find the standard error and conduct the tests of hypothesis indicated in the previous slide. Now note that this table arose from a cohort study. So once more, interpretation of the risk ratio. Firstly, it suggests that patients treated with Ramperil had a lower risk than untreated patients, as the risk ratio is less than 1. The drug induced a 22% decrease in the risk of CV events. So risk ratio of 0.78 implies a decrease of 1 minus 0.78, which is 0.22 or 22%. If we calculate the 95% confidence interval, it is possible to show that this is given by 0.7 to 0.86. Another common class of studies which is somewhat logistically simpler than a cohort study is the case control study. So here we are looking at cases which are people who have AV fistula thrombosis, and controls, which is people who do not have AV fistula thrombosis. That is, we have selected a group who are diseased and a group who are non-diseased, and we are looking back in time to see how many of the diseased group had the exposure, which in this case is thrombophilia, and how many did not. Now, if you look at the panel on the left of this slide, we see that the odds ratio is given by AD by BC, which is 59 by 48 by 122 by 190, which turns out to be 1.91. The risk ratio correspondingly is given by 59 by 181 divided by 48 by 238, which turns out to be 1.65. Now let us suppose that we conducted the same study except that we increase the number of controls. So instead of 122 and 190 controls in the two exposure groups, we instead had double the number, which is 244 and 380. So in this case, the odds ratio is now 59 by 48 by 244 by 380, and it turns out that the odds ratio is unaffected by this multiplication and remains at 1.91. The risk ratio, however, is now 59 by 303 by 48 by 428, which is equal to 1.77. So this means that the risk ratio is not an acceptable measure to use in case control studies, and the reason is that we do not know the denominator of the risk ratio. That is, we do not know the size of the target group from which these cases and controls were derived. In the absence of this additional information, we cannot calculate the risk ratio, and thus, whenever we have a case control study, it is necessary to use the odds ratio. The risk ratio and the risk difference cannot be obtained and hence cannot be used. Absolute differences. Absolute differences, the risk ratio we have seen before is considered an absolute difference. It is also sometimes referred to as the absolute risk reduction. It is the difference between the incidence proportion of a disease or event in the control group and the corresponding incidence proportion in the treated group. The risk difference for cardiovascular events between patients on placebo and on Ramperil is 0.18 minus 0.14, which is equal to 0.04. So, the interpretation of this is that there is a 4% absolute risk difference which is attributable to the effect of Ramperil. A related measure which is used in the epidemiologic literature is the number needed to treat. So this is derived as follows. On the basis of the risk difference, it is possible to calculate the number needed to treat, that is the number of subjects we would need to treat with Ramperil to prevent one adverse event, which in this case is a cardiovascular event. Note that the inverse of the absolute risk difference is 1 over 0.04, which is equal to 25. The interpretation of this is that we need to treat 25 patients with Ramperil to prevent one cardiovascular event in 5 years. The inverse of the risk difference thus is interpreted as the number needed to treat. The obviously ideal value for the NNT is 1, which would be obtained if the difference was 0. That is, if the risk in one group was 1 and the risk in the other group was 0. This is, however, just the ideal situation and is used as a benchmark. The importance of the NNT is that it presents information on the risk difference in a way which gives clinical relevance to the data. So if the number of events had been 65 in the Ramparel group and 83 in the placebo group, the NNT would have been 250, while the RR would have remained unchanged. So the NNT is more responsive to the number of events. Another related measure is the attributable risk. The attributable risk is the portion of the disease incidence in the exposed that is due to the exposure. That is, the incidence of the disease in the exposed that could be eliminated if the exposure were eliminated. It is measured as the risk or incidence in the exposed minus the risk or incidence in the non-exposed. Often we prefer to use this in the form of a percentage. So the attributable risk percentage is the proportion of disease incidence in the exposed that is due to the exposure, and it is calculated as the attributable risk divided by the risk incidence in exposed into 100%. That is, the attributable risk percentage is equal to RR minus 1 divided by RR into 100. In this module, we have reviewed the concept of the risk difference and the risk ratio, but from a slightly different perspective than that from the statistician. That is, we have looked at these concepts from the framework of epidemiology. We have defined the basic unit of epidemiologic analysis, which is the 2x2 table, which arises when we have a binary exposure and a binary disease, and we wish to quantify the association between the two. That is, we wish to see if the incidence of disease in the exposed group is different from the incidence of disease in the control group. It is possible to do this in several ways. We can look at absolute differences in the exposure, in the incidence in the two groups, or we can look at relative differences. Accordingly, we define the risk difference as an absolute measure of incidence, or we can define the risk ratio as a ratio measure of comparison. So we have defined these two measures, seen how to estimate these from the tables, and in fact the estimators which we have presented are maximum likelihood estimators. We have seen how to perform statistical inference based on these measures using wall tests and standard errors which have been derived using the delta method. We have also seen how to derive confidence intervals, and I have pointed you to several references should you be interested in further details on this. For the sake of comparison, we have defined an alternative measure which is also very common and very popular, which is the odds ratio. And we have seen that one reason for the popularity of the odds ratio is that the odds ratio can be calculated from the cohort study as well as from the case control study, whereas the risk ratio and the risk difference cannot be obtained in the situation where we have a case control study unless we have more information on the size of the target population. Finally, we have defined two related epidemiological concepts, which is the number needed to treat and the attributable risk, which are based on the risk difference and the risk ratio, but they present two ways of presenting the information to an epidemiologist, which makes it easier for them to interpret the data from a clinical perspective.